So in the previous classes we were talking about intra-domain routing, and we talked about distance vector and link state routing. Okay, so examples of link state routing, actual protocols are OSPF and ISIS. Distance vector we said there is RIP. Okay, so all these protocols are essentially going to find the shortest path. So given any particular network and given some weights between different links, okay, whatever it is, maybe these are the weights. Okay, so if this node sends out a packet, automatically it will go on the path to the destination which is shortest in terms of sum of the weights along that path. Yeah, and of course you've studied in your algorithms class, and essentially those same algorithms are implemented, but in maybe in a distributed setting. Okay, they are implemented here. The question is, what should these weights be in practice? How do we choose these link weights? And if you were a network engineer, you might come across this problem, and so if you choose a low weight for a particular link, there's a higher chance of it getting used for a path from one node to the other. But what should that weight be? Suppose I choose a particular weight here, and then let's say this is A and this is B. Maybe all the data that is meant to go from A to B will let's say go along this path. It might go along this path, and none of the packets from A meant for B will go along this link. Okay, and you may have a situation where certain links are underutilized, not much data goes on them just because of the weight you set there, and most of the data goes along some other links where the link weights have been set very low. Okay, so what should we choose them to be? Okay, that's a non-trivial problem, and you might think that if this is a this has a low link capacity, maybe this is 10 megabit per second, whereas this is a gigabit per second, then obviously you want to give a lower weight here to the higher speed link so that there's a chance that it will get used. Okay, but what if that gigabit per second link gets congested a lot? What if these queues that are there at these routers start getting filled up even when you have a high speed link? Then maybe the latency on that link goes up. So then what do you do? Should you increase the weight, or what should you do? Right, so these are questions that came up in the original ARPANET, and let's study what they did in the ARPANET in the early stages of the internet. So in the ARPANET, in the very first network which evolved to the current internet, the data rates of course were not so high. So they had 56 kilobit per second links. And 9.6 kilobit per second. So these were the two speeds that they had for the links in their network. And of course we're talking about the late 60s, and things have evolved so fast from then. So just as an anecdote, when I was a student in IIT Madras in the 1990s, the whole of IIT Madras had only a 64 kbps link. That was when the internet first came to India, as late as 96, 97, right? And my lab, the networks lab which I was in, of course I was a student doing a project there. We too had a special 64 kilobit per second link, and we were very proud of it, that our lab had a link with as much data rate as the whole of IIT Madras. Okay, but those were the early days of the internet. Internet was just coming out, and of course, things have increased exponentially since then. Of course, so the early internet, of course, had links something of speed compared to this, but there were also slower links. So in addition, some of the links were terrestrial and some of them were satellite links. Okay, so a satellite link, you may have an antenna like this, and it let's say that there is a satellite out there up in space. So the satellite gets data and it forwards it to another ground station, let's say. So this would be a satellite link. But there were also terrestrial links which had these two speeds. Okay, so essentially we are looking at 4 types of links if we combine these two speeds and these two types. And the question is, in this sort of a network consisting of these 4 types of links, what sort of weight should you set for them? Okay. So of course initially they were experimenting, so they said let's look at one of these links. So let's zoom into the routers. So there's a queue here, we said an output queue, and okay, there is a output queue here, and of course there is some buffer over here into which the data is written as the packets come. So what should the links weights be, because this is just one link in the whole graph, and what sort of weight should I put there? Okay, so based on the weight, automatically the shortest paths will be determined and so on. So what they said is let's use latency. So this was the first idea. Use latency. So what do I mean by latency here? So suppose this is the size of the queue and I put a packet in here. I want to know what is the time the last bit of this packet actually reaches this particular router. Okay, so the latency of a packet on this link is essentially the queuing delay, okay, the time for which this queue empties. So this queue is everything ahead of this packet. So let's say this is the packet that we put in there. So it's the queuing delay Okay, so once the queue gets empty, that's what we are calling the queuing delay. The first bit of this packet gets sent on this particular link, and that first bit takes some particular delay to go here, and let's just call it the speed of light delay. And we want to know the time at which the last bit comes over here, enters this particular router. And so suppose the packet size is p bits, and let's say that this is data rate is c bits per second. So essentially we are going to have what's called the transmission delay, which is the packet size in bits divided by c. Okay, so it's the sum of these three delays. Okay, so this is the latency, and they wanted to use that. Okay. So what, I mean, you might think, what is this going to be? I mean, because let's say that this is the queue size, but then let's say many other packets come in. Each of them is going to face a different delay, because even if they are of the same size, the speed of light and the transmission delay are going to be the same, but the queuing delay will vary. So this latency of packets keeps changing, and should we change the link weight for every packet which comes in? That doesn't make sense. So what they said is, you take a time window and for all packets in that time window, you calculate these latencies and take an average. And latency of all packets in the window, and I should say average of those, is the link weight. So what this means is that over time, let's say we divide it into particular windows, and there are many packet arrivals at that particular queue. So I'm just plotting the packet arrival times. Right. So for all these packets, you compute this, the time taken essentially to go across the link, and you take an average of those, and that gives you the, let's say, the cost of a particular link. So why would this maybe be a reasonable way to get the link weight? So let's think about it. So suppose this C is small. Suppose it's 9.6 kilobit per second instead of 56 kilobit per second. Then obviously this transmission delay is going to be more. Okay, so the smaller C is, the larger this component is going to be, which makes sense. You want to give a higher weight to a lower speed link because you want to give preference to higher speed links to be used. Okay. And also, of course, the queuing delay, if let's say there's a lot of congestion in the network on a particular link, then the queuing delay would be high, in which case you're giving a higher weight. So you're saying use links which are less utilized, where the queues are relatively empty, compared to links where the queues tend to get full quite often. So intuitively it makes a lot of sense, but when they did this, they found there were lots of issues with it. So there were several issues with this particular method, and let's list some of those down. So first of all, they found out there were lots of oscillations. So meaning that under heavy load, there were a lot of routing path oscillations. And why would that happen? Let's go back to this example. So let's say we put a low weight here, and all the data keeps going, let's say from A to B along this path. But then maybe the queues over here get full, and so we update the link weight. So we increase the link weights here, so that according to whatever idea we just had. And because of that, these link weights, let's say, get high, and so the shortest paths are recomputed, and let's say this becomes the shortest path from A to B. Okay. So then what happens is all the data will go, instead of going along this path, now will go along this path from A to B. And now the queuing delays along this path will increase, and the queuing delays here will decrease because packets from A to B are not going this way. Okay, so the link weights here are going to decrease, and here now the link weights are going to increase because the queuing delays are high. Right, and then what might happen is again shortest paths are recomputed by the protocol, and because of which the shortest path will shift from here to here, because the link weights have gone up here and they've come down over here. So you could have this sort of oscillation. The path flips from one to another just because the link weights are changing too often. And this is not always a good idea. Okay, first of all, the latency is going to change between A and B very drastically. It's going to be flipping quite a bit. And you may even have something like a packet reordering. So suppose you're sending 10 packets from A to B. The first 5 packets may go this way, and the rest of the 5 of them may go this way because the shortest path has flipped from here to here. Okay. Also, if you keep changing these links quite often, the link weights quite often, you may end up with routing loops of some kind. Okay, so if the paths have converged, then there is no problem. That if you send out a packet, it will definitely take the shortest path from A to B. But if there is a routing loop, I mean, if not everybody sees the same information, they are all continuously recomputing routes, you may end up with loops. Okay, because for some reason, not everybody has the same picture of the network. Not everybody has seen exactly the same weights. Okay, so oscillations are not a good idea for these various reasons. Okay, so routing paths oscillate, and the reason is that queuing delays go up, and this leads to increased link weights, and then essentially this leads to new shortest paths. And then on these shortest paths, the queuing delays go up. Okay, and certain other links, the queuing delays will go down. Okay, and maybe I could say that so queuing delays go up, let's say on paths used heavily. Okay, and this keeps continuing. You keep computing new shortest paths. Okay, so why is this bad? Well, because the end-to-end latency what I mean by end-to-end is example from A to B in the network keeps varying. And so applications using sending packets from A to B will see very varying amounts of latency, so that may or may not be good. So it may affect the application layer performance. Okay. And besides that, it could lead to reordering of packets. So this is A and this is B. So I'm sending packets, let's say 1 to 10, and just labeling them 1 to 10. 1 to 5 may go this way, and 6 to 10 may go this way. And it may happen that this path is actually has lower latency than this one. Okay, maybe the queues were filled up here. So the packets, when they arrive here, it may be 1 to 6 all the way to 10, and then 3, 4, 5. Okay. So this is what I mean by packet reordering. That these packets overtook packets 3, 4, 5 because they came along this different path. And this reordering may also affect application layer performance. I mean, maybe a particular application requires packets to be delivered in order, and then that is a problem. The issue is like what I had mentioned a short while earlier. We could have routing loops. So the protocol itself, like a link state routing protocol, shouldn't give routing loops, but that is when we assume that the weights are fixed and then the routing paths have converged. Okay, but if you have a large network and let's say something like this, and maybe let's say that this particular node thinks that this is the shortest path all the way to this other node. Okay, but the links weights are changing so fast that so he will send, of course, the packets here, but this person hasn't yet finished computing the shortest paths with the latest link weights, or maybe he hasn't received certain link weights. So his information is a little bit stale, so he may think that this is the shortest path. Okay, even though A thinks this is the shortest path. And maybe this particular node thinks that the shortest path actually is this way. Okay, so he will maybe send the packet back over there. Okay, so if you want everybody to have the same link weights for all the links in this graph, otherwise there's a possibility of having routing loops. And if we have link weights changing so often, then that is a problem. This is quite realistic. Okay, so this was a problem, one of the problems that they faced. So another problem that they faced is that the range of link weights was very large. And because of this, we'll see that because of this, some links were penalized too much. And this is due to very high weights. Okay, so what did they find? So suppose suppose there is a path here between two nodes. Let's say there is a direct link. This is like a toy example. This is 9.6 kilobit per second. And suppose there was another path consisting of many 56 kbps links. Okay, so what they found is that in certain situations, this 9.6 kbps link might actually have a weight corresponding to 126. Suppose there are 126 of these. Okay, in certain situations, depending on the load and other things, this 9.6 kbps link had the same weight as 126 56 kbps links put together. Okay, just if you think about it, where does this link speed come in? So it comes in two places. One is in this transmission delay and also in the queuing delay. Because if the link is slow, it's going to take longer to empty a queue of a particular size. So they found that 126 links of 56 kbps had same weight as a single 56 kbps. Single 9.6 kbps. Okay, depending of course on the traffic load conditions and so. And practically, does it make sense to do this? That was what they were thinking. So if this was the situation, packets from A to B would be routed along this path rather than this one. That could happen in certain situations, which doesn't make sense. I mean, A is directly connected to B with this link. Why shouldn't I use this link? Why should I send it over this longer path consisting of 126 links? It doesn't make much sense at all. So essentially the range of weights of links was too much. This 56 kbps link, that means, was less than 1/100th of the weight of this 9.6 kilobit per second. So they wanted to not have these sorts of have these sorts of problems. Okay. So this link is essentially penalized too much. It's given a very high weight compared to these other 56 kbps links. Okay. So okay, I'll just write this. This is a heavily loaded link. Then they found that satellite links are penalized too much. So now let's say that we look at a different scenario where A and B have let's say a 9.6 kbps terrestrial link. Okay. So here of course we are assuming the same type. If this is terrestrial, these are also terrestrial and so on. Okay, but here let's say that we have a satellite link, and this is 56 kbps. Now here they found that the 9.6 kbps terrestrial link actually had less weight than this 56 kbps link under certain conditions. And why is that? So the reason is that the speed of light delay is quite high over here. Okay, going all the way to the satellite would be, here we have hundreds of kilometers. The satellite is up in the sky. This may be, a few tens of kilometers. So because of that, even though this has a higher data rate, the cost of this particular link is going to be much higher than the cost over here. Okay, so this is actually has less weight than this link. Okay. So what seemed a very reasonable way of assigning weights to links using these latencies turned out to have lots and lots of problems. Okay, and so they tinkered around and they came up with a set way of deciding link weights. So they used this particular graph, which I'm going to draw now. So on this axis I'm going to plot what is called utilization. That is what is the utilization? Well, it's a fraction of link capacity which is used. So of course this changes over time. So what you do is you look at a large enough time window. Let's say I look at a link for 1 hour. If it's let's say a 100 megabit per second link and only 50 megabit per second is used, then I would say that it has utilization 50%. Okay, so there is some time window implicit over here, right, while when we measure the utilization. So 0 means there's no packet going on a particular link, so queues and everything are empty, and 100 means the link is highly utilized. Okay, so here on this y-axis I'm going to plot the link weights which are going to be assigned, and we are going to do it for all 4 different types of links. So clearly if the link utilization is very high, I want the link weight to go up. So what they said is let this be, let's say 30, 60, 90, 120, 150, and roughly this is 225. Okay, so what they said is for a 56 kilobit 56 kbps terrestrial link, of course you want to give it the highest priority because the latencies are low and also the link speeds are high. Okay, so they said if the link speeds are low, I just give 30 as the weight. Okay, and when it goes a little bit above 50%, then I start linearly increasing the weight. Okay, and so around 90. So okay, so it stays constant and then I increase slowly. Okay, this is a straight line from here to here. Okay, so this is roughly 90. What about 56 kilobit per second satellite link? Okay, so we want to give it a higher weight. So let's say it's something around over here. Okay, so they said that if you have two 56 kbps links, one is satellite and one is terrestrial, then you prefer the terrestrial one to the satellite one. Okay. And this is 56 kbps terrestrial. So what about the 9.6 kbps links? So they gave them higher link weight. So they said what we are going to do is we are going to increase after this all the way to roughly 220, 225. Okay, so this is roughly 225 is the link weight at 100% utilization, and 9.6 kbps satellite link would have of course a higher link weight, around 140. This is satellite and this is 9.6 kbps terrestrial. So they said let's not actually measure queuing delay and based on that set the weights. Let's look at the utilization over some large period of time, and we just look up this particular graph, and based on it we will set the weights of the links. Okay, and that took care of lots of problems. Okay, so the range of weights was at most 7. So if I compute the this is the maximum weight that any link could have, and this is the minimum. And the ratio was about 7. Okay, so it wasn't 120 or something like that which they had earlier, right? And at the same time, 56 kbps satellite link was preferred to this one. So this is this particular link is referred to this particular link. Okay, and you can see essentially we are addressing all these various problems in that way. Okay, so how are we avoiding routing loops? Well, because we don't keep changing the weight so often. This is measured only over a very large time period. So weights are changed infrequently. So what about today? How do engineers actually set these link weights? So some protocols by default have particular weights. So OSPF, Open Shortest Path First, which is a link state routing protocol, gives these weights. So the weight of the link is given by 10 to the power of 8 divided by the link speed. So the link speed is just the link capacity, the maximum data rate at which you can send on a particular link. This measured in bits per second. So if it's 1 megabit per second, the weight would be 100. If it is 10 megabit per second, it is 10, and so on, right? And of course, if it's 100 megabit per second, you have 1 here, but if it's a gigabit per second, you would go less than 1. And they decided to allow a maximum of only 1 as the link weight. Okay, that's a particular choice they made. Okay. So if you don't set it manually, then this is what the routers would decide is going to be the link speed. But it doesn't take the utilization into account. Okay, so it makes sense to have some other method to actually set the link weights. Okay, and how do we do it? So I remember I once went to something called a Network Operations Center. They're called NOCs. This was quite a while back, around the year 2000 or 2001 maybe. And this was at AT&T, which at that time was one of the largest internet networks within the United States, right? So what these people in the Network Operations Center did is that on very large screens, they actually saw the whole map of the US, which would look something like this, and it actually had so almost like an animation, showing what are the links between various cities, the large cities. This is the East Coast, whatever, New York. Here you may have LA and so on. So they could actually see what is the utilization on different links, okay, based on the color coding. So they knew the link capacities and the utilizations and so on. And the network engineers, using their own intuition, would change the weights. So they saw that this was getting, let's say, very red colored because of high utilization. What they would do is they would increase the weights here or maybe decrease the weights here a little bit so that the traffic would get rerouted. Okay, so at least at that time they were just using intuition. They weren't using a specific algorithm, and they were manually changing the weights a little bit so that utilization would come down in one place and maybe get shifted somewhere else. Okay, the traffic would get rerouted. Right, so That was how it was being done then for the very important network in the US. So I'm not sure if they've upgraded to some particular algorithm like this. But yeah, it's a good idea to keep an eye on a network like what they were doing over here, because you never know what might happen suddenly. Maybe a link goes down or something like that, and in which case you would have to drastically shift data from one set of paths to another set of paths. Okay. So large networks will always have something like a network operations center where you have people continuously monitoring the status of various links and so on, and they have to take remedial measures in case something goes wrong. Okay, so this was a little bit about how to set weights, and in the next few topics we're going to cover is first of all the IP addressing, and after that we will actually look at protocols like ARP, which are very basic protocols where given the IP address you want to find the MAC address of the corresponding machine, and after that we will go to BGP, which is really the glue which gets the entire internet together, which sort of ensures that packets will go from one end to the other, even despite different autonomous systems using their own routing protocols with their own routing metrics.